Electrostatics, what you called in Science 9 static electricity. Some of this will be review, especially if you had a Science 9 teacher who was really into the physics stuff. He might expect you to remember some of the stuff you learned in Science 9, so be prepared, says your former Science 9 teacher to some of you. But I'm going to assume, Nick, that you've forgotten it all. I don't know why I picked on Nick for that as one of my students that I taught, but yeah. And so we're going to start out really basic. Matter is made up of atoms. That's actually a tremendously profound statement. Our model of an atom, and this is not what an atom looks like, but as a good model, we're going to pretend that atoms have a central nucleus and that they have these little dots called electrons that orbit around them. That's not what's occurring, but by pretending that's the case, Hannah, that will allow us to explain a fair bit of stuff. But it's a model and it's inaccurate. The same way we've often ignored friction, or our Atwood machine was a massless, frictionless pulley, so it'll work. When atoms bond together to form solids, the electrons can be tightly bound to the atoms, especially in covalent solids like glass. These are called insulators. They will not allow electrons to travel very easily, but they will allow the buildup of electrons very easily. Most of the time when we're talking about static electricity, that occurs when you have an insulator, because you can build up electrons, storing them on an insulator, and they can't travel anywhere. They can also be free to move around, as in metals, and these materials will be called conductors. Typically, we're talking about ionic compounds or pure metals. All subatomic particles, protons, electrons, and neutrons, have a property. And we've given this property a name. We call it charge. Most of these names, many of these names came from Benjamin Franklin. Benjamin Franklin did some experiments with electricity, and he used military terms. So you charge a cannon with gunpowder. He felt that charge was, by the way, that's also why it's called a battery. The same way you have an artillery battery, a battery of artilleries, a battery to him was a whole bunch of charge put together. So one big problem you're going to hear me go on a rant about is that Benjamin Franklin is also who decided what's positive and what's negative, and he got them backwards. He named them wrong. Protons should be negative. Electrons should be positive. If we could change one thing as electrical engineers, if we go back in time, we would go to Benjamin Franklin and we'd say, no, call that one positive. It would make the math much nicer. You'll hear me go on a rant about that several times this year. It's charge that's responsible for both electricity and magnetism. In fact, we have learned that electricity and magnetism are two sides of the same coin. They're one big force called electromagnetism. So we'll talk about electromagnetic waves and things like that. Some basic facts about charge. There are two types of charge that we call what and what? I already said the words. Positive and negative. I tend to abbreviate. So my abbreviation for positive is a plus sign and then a VE next to it. That to me is the word positive. If I just see a plus sign, I go looking for an equation. You can use your own abbreviation, but I use a plus VE and a minus VE. Those are my abbreviations for positive and negative. Does anybody know the units for charge? What do you measure charge in? I'll give you a hint. It starts with the letter C. Some of you might not be clever enough to look at the title of the lesson and figure it out. We measure it in coulombs. 1 coulomb is massive. 1 coulomb would kill you if you absorbed it all at once. 10 coulombs probably wouldn't just kill you, it would kill you in the gruesome horror movie, skin on fire, melting clothing, sparks everywhere kind of way. Most of the time, we'll be dealing with micro coulombs, which are 10 to the negative 6 coulombs. Charge is represented by the letter. We can't use the letter C because what's a lowercase c? It's very special. Speed of light, okay? Uppercase C, for those of you who are wondering, I think is heat. Nate, do they use the letter capital C for heat in the AP Physics course? They use what? For heat? Really? I learned something new. Or maybe it's an American course and they screwed up the units, because that wouldn't surprise me either. Oh, did I say that out loud on the internet? Sorry. Uppercase Q or lowercase q for charge. In fact, I'm going to do something similar that we did with gravity. I'll use an uppercase q for the big planetary charge and a lowercase, like the nucleus, and a lowercase q for the tiny charge that's orbiting the planetary charge. Why q? Well, charge is quantized. It's one of the areas where the term quantum physics comes from. What does quantized mean? When something is quantized, it comes in finite chunks that can't be broken up. A good example is our money system. What's our fundamental unit of money, even though we don't make the coin anymore? What's the smallest unit of money our system allows for? The penny, 1 cent. And every other coin or bill is made up of multiples of 1 cent. A dime is 10 cents. A dollar is 100 cents. There is no 22.57 cent coin. Doesn't exist, and our system doesn't even allow for it to exist. If you're doing some math and you end up with that, the system will automatically bump 22.57 to 23 cents. In fact, now we're even starting to bump into the nickel range, but we're still based on a penny. So, with money, there is a smallest unit, the cent, and any amount of money can be broken down into a certain number, a whole number of pennies. With respect to charge, there is a smallest unit of charge called the elementary charge. It's on your formula sheet. Go find it. So it's going to be where all that data is on the back page, where all the constants are. The symbol for the elementary charge is a lowercase e. How big is it in coulombs, please? Graham.
Plus or minus.
Why plus or minus? We'll talk about that. Keep going.
1.6 times 10 to the negative 19 coulombs.
Positive, if it's a proton, the charge on a proton is positive 1.6 times 10 to the negative 19 coulombs. Negative if it's an electron. The charge on an electron is negative 1.6 times 10 to the negative 19 coulombs. What's the charge on a neutron, Graham?
Neutron.
You know what? That suggests that maybe a neutron is formed when you take an electron and a proton, and inside a star under tremendous pressure, you smoosh them, you fuse them together. I wonder if a neutron is actually made up of a proton and an electron that have been fused together. It is, along with some other subatomic particles. In fact, in radioactive decay, what often happens is a neutron can decay and it shoots off an electron as what we call beta waves, and you end up with an extra proton, and that's how one element can decay into another element. We suddenly got an extra proton that we didn't have before. All larger charges are multiples of the elementary charge. So if you want to know the charge on something, it's the number of protons or the number of electrons times 1.6 times 10 to the negative 19. I should be careful, Jacob. Actually, this would tell you how many extra protons or neutrons you have. You might have a trillion protons and protons and neutrons, protons and electrons. You might have a trillion electrons and a trillion protons. That's a charge of 0. And so if you were finding that you had 5 extras, what that would be telling you is you had 5 extra charges that weren't canceled out by their corresponding negative charge. Technical comment, if you're nerdy, you might be aware of particles called quarks. Those have charges of 2/3 of an elementary charge, plus or minus, and 1/3 of an elementary charge, plus or minus. So we have since learned that it turns out in the quantum world you can be smaller than a penny. But we're going to pretend those don't exist to keep the math nice. Okay? In this course, you have a data page right where you have the elementary charge. I think there you'll also see the mass of an electron. It's 9.11 times 10 to the negative 31. You'll also see the mass of a proton. It's 1.67 times 10 to the negative 27. And I don't know if I gave you the mass of a neutron. Neutrons don't interact with charge the same way, and so we're going to tend to ignore them. But you notice that the mass of a proton and the mass of a neutron are almost identical, because I told you that a neutron is made up of a proton, an electron, and some other stuff. The other stuff makes up that 0.01 times 10 to the negative 27 right there. What's also cool is some of that other stuff is actually mass gained due to a gain in energy due to E equals mc squared, the fusion process that goes on. What's the 10 to the on the electron? 10 to the negative? Anyone can read it. What's the 10 to the on the proton? 10 to the negative? 27, take away 31, 10 to the fourth. Proton roughly weighs 10,000 times more than an electron. Electrons are really light. Not the lightest thing in the universe. Possibly the lightest thing in the universe might be neutrinos. We only found out 3 years ago a Canadian won the Nobel Prize by showing that neutrinos have mass, but it's beyond our ability to measure. We know they have mass because they're affected by time, and Einstein showed that only objects that are affected by time, or only objects that have mass, are affected by time. So we know neutrinos have a mass. We don't know how big. Hashtag nerd trivia. The data page, Nick, does not explicitly list the charges of the particles. So this you need to know, and I think most of you do know this. The charge on an electron is negative 1.6 times 10 to the negative 19 coulombs. And we often use an E with a little minus sign next to it as our symbol for an electron. We often use a P with a plus sign next to it as our symbol for a proton. Its charge is positive 1.6 times 10 to the negative 19 coulombs. What was the charge on a neutron? 0 coulombs. So, let's do a tiny bit of calculating, but I think we'll try and do this in our head. Although this does not need to be memorized, you might recall from Science 10, when you look at radioactivity, that an alpha particle was actually a helium nucleus. It had 2 protons, 2 neutrons, and no electrons. What's the charge on this particle? Well, charge is going to be the number of charged particles times the elementary charge. Aisha, how many electrons does an alpha particle have according to this description? How many neutrons? Oh, you know what? Wait a minute. What's the charge on a neutron? So who cares about the neutrons? How many protons does an alpha particle have? So the charge on an alpha particle would be 2 times 1.6 times 10 to the negative 19. You might even be able to do this in your head. What's 2 times 1.6? You know what? It's going to be 3.2 times 10 to the negative 19 coulombs. If I'm running a particle accelerator and I detect a mystery particle with that charge, my first thought would be, probably an alpha particle. Then I'd try and find a way to measure the mass. If it weighed as much as 4 protons, then I'd say, yeah, that's an alpha particle. I got 2 protons and 2 neutrons. I think I've narrowed down what it is. For a conductor, electrons flow freely and easily. For an insulator, the electrons can't flow, but the orbits can shift slightly. You can get the electrons to gather mostly on one side of an atom. We call this phenomena polarization. Hopefully nothing so far has been new. Electromagnetism is one of the 4 fundamental forces. Charges exert a force on each other. In the same way that objects with mass send out a gravitational field, like the invisible tentacles of an octopus in all directions that exert a force on other objects with mass, objects with charge send out an electric field, like the invisible tentacles of an octopus in all directions, and they will exert a force on other charged objects. You might recall from Science 9, like charges will blank, unlike charges will blank. Like charges repel. unlike charges will. You absolutely need to memorize that, although I think you will. Like normally, if it was something you absolutely need to memorize, I'd tell you to put a star or highlight it. You'll memorize it if you're halfway paying attention. So here I have two negative charges. Are they like or unlike? So if I drew kind of a free body force diagram, I would have an electrical force pushing this one down and an electrical force pushing that one up. Compare that to the second diagram where I have unlike charges. They're attracted. I would have an electrical force pulling the positive charge to the right, and I would have an electrical force pulling the negative charge to the left. This behaves an awful lot like gravity. Here's the big planet pulling in the asteroid. This behaves differently from gravity. And so one of the things you're going to notice when we look at electrostatics is our equations will look really similar to the ones we just finished with using in gravity, except stuff can also fall up. We'll have to make a little adjustment there. One of the safest places to be inside a lightning storm is inside a metal, during a lightning storm, is inside a metal car. Why? If you were in my physics science 9 class, you're not allowed to answer yet. So those of you that I didn't teach in Science 9, why is a metal car so safe to be inside of during a lightning storm? Yeah. Yeah, we're making a hypothesis. This is science.
Because it's a conductor and allows the electricity to be grounded?
Sort of. Gabe said it's because it's a conductor and allows the electricity to be grounded. First of all, I'm happy nobody said because of the tires. Because the lightning has just managed to jump a kilometer from the sky to the car. I assure you it can jump this much further in spite of the tires just fine. It can jump the remaining half meter or quarter meter. A car is made out of what? Most cars are made out of, looking for word being the letter M, metal. So you ready? I'm going to pick on someone for the rest of this unit. They got to be someone who's pretty much never away. I already picked on Nick for one of these, didn't I? Okay. Gabe, this is going to be your cue. Like charges.
Oh, sorry.
Like charges. Say it again. Like charges. One more time. Like charges. So when the car absorbs all of these extra electrons, trillions of them, they want to repel each other. And by that I mean they want to get as far away from each other as they can. And because the car is metal, they can move through the metal frame. What's the furthest they can get away from each other? On the very outside of the car. That's the furthest they can get away from each other. Where is the passenger sitting? On the inside of the car. Put your pencils down, look up. So let's see if we can write down an explanation here. Like charges. Gabe? The electrons, I'll use E minus, gathered on the car, gather on the outside, keeping the passenger safe. Did anybody hear what they called this particular thing? It began with the letter F. It was a type of cage. It's a Faraday cage, named after Michael Faraday, who first proposed it. Michael Faraday said, you know, it sounds counterintuitive, but if you wore a suit of metal, that would prevent you from getting shocked around electricity, as opposed to wearing an insulating suit. A Faraday cage would be a better way to go. I'll go on a Michael Faraday rant later on this year because he's one of my nerd heroes. One of the things that we'll often use to try and understand a particular set of phenomena is a charge diagram. So here's what this says. A negative rod is brought close to an insulating ball. The ball is first attracted and then repelled by the rod. Explain why this happens. Okay. I'm going to do a charge diagram. The diagram, of course, is going to be inaccurate because if I was trying to be accurate, there'd be several trillion protons and several trillion electrons and a few 100,000 extra electrons. I'm going to try, well, it's going to look like this. First of all, to show that this ball is neutral, I'm going to put a single plus and a single minus on it. I'll put the minus right there so you can see, but try and draw it on the ball if you can. But really, each of those represents like a trillion. Okay? Trillion protons, trillion electrons were balanced. This rod here would actually have a few positives and then be mostly negative, but I'm just going to show it as all negative. So I'm going to go negative, 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 like that. All right, we bring the rod in, or the little piece of plastic in, close. What happens? Gabe, like charges. And so all of the negatives, or at least a number of the negatives that are in the ball, they move to the right side. The positives in the ball stay on the left. And so what you have near the little plastic rod is positives here, negatives here, and you have unlike charges attracting right there. That's why it initially gets attracted, because those positives are closer than these negatives, and so they apply a stronger attractive force than these negatives apply a repulsive force. Okay? However, as soon as we touch, because the electrons here are repelling each other, a bunch of extra electrons jump across. There's still some positives there, but a bunch of extra electrons jump across. Now, this ball is no longer neutral. What's the charge overall on this ball now? Positive or negative? What was the charge on the rod? And it has extras still, so now, like charges, and you end up with still some positives on the ball, but the ball is overwhelmingly negative. Because we had to come in contact, we call that charging by conduction. We actually transferred electrons from one object to another by touching them to each other. You can also charge an object without touching it. How many of you have a phone that has a wireless charging system on it now? You do? Okay, so that's using an induction charger. We call that charging by induction. Or how many of you have an electric toothbrush? Okay, that charges through induction. If you look underneath, there's no metal contacts. That would be a bad thing to have around all that wire. It's charging through induction. You can, with some cleverness, set up a system where you can charge an object without touching. Here is one such system. This is not how I would design your phone recharging system, but it shows you with some cleverness we can do it. Suppose we have two metal spheres and they're neutral. I'll symbolize that by having 2 protons, 2 electrons, 2 protons, 2 electrons. But again, Justin, you can think 2 trillion protons and 2 trillion electrons. If I bring in this negatively charged rod, like charges, and so all of the negatives, or at least many of the negatives, will get pushed to this metal sphere because in the metal they are free to move. And that will leave behind some positives here. Now, I have not touched this rod to the metal. I have not transferred any charge, but I have moved charge around inside the metal spheres. Now, if I grab the base of this right-hand sphere and I just slide it to the right while the rod is still there, so I still have a negatively charged rod. If I slide it to the right, I would have that situation. And now, Hannah, if I take the rod away without touching the metal spheres, I was able to move them from being originally neutral to each of them are now charged. We call that charging by induction. And again, that's just to show you an example of how we can do it, Maggie. The system for your phone, Ethan, or your electric toothbrush, much more efficient. But even so, as far as I know, I don't think we'll ever have wireless charging or induction charging as fast as conductive charging. It's still a slow process. You've probably found for your phone, plugging it in is still faster. Yeah, and as I understand the technology, unless they've come up with a completely bizarro way to do things, that will always be the case, I think. But there's some good potential here. So, for example, for electric cars, why don't we just put an induction mat on the floor of your garage? And so when you park on it, or better yet, why don't we build parking lots with induction mats so that while you're parking, your car is charging? Ooh, better yet, what if we started building induction mats into our roads so that as you're driving, your car is recharging? Food for thought, right? Not quite as easy as I'm making it sound, but the garage one is. Certainly you could put an induction mat into your garage. So you could see that the little piece of plastic was applying a force to the styrofoam ball that was hanging. Graham especially could see it dancing around. If I'm applying a force, there must be an equation. This equation is called Coulomb's law because Coulomb did the experimentation. He found that, like for gravity, there was an inverse square rule. If there was an r squared in the bottom of the equation, if you went twice as far away, it was 4 times weaker. If you went 3 times as far away, it was 9 times weaker. If you went 4 times as far away, it was 16 times weaker. Here is the equation for electric force. I use a subscripted E for electric as opposed to a subscripted G for gravity. And it's equal to K, Q1, lowercase k, Q1, Q2 over r squared. What equation does this look an awful lot alike? There's an r squared. Force of gravity. The fact that this looks so much like gravity and the fact that there is positive and negative charge, physicists have wondered, was there positive and negative mass? Is there an anti-gravity mass? We haven't found it yet. In gravity, this was big G, which was a constant. Lowercase k is also a constant. What is it? It's on your formula sheet. 9 times 10 to the 9th. If we didn't put that there, this would be coulombs squared per meters squared, which I'm telling you is not newtons. So to change these and get an answer in newtons, we multiply by 9 times 10 to the 9th. What are the units on that?
Units times meters squared over coulombs.
Yeah, whatever. 9 times 10 to the what? 9 times 10 to the what? What was the big G? 6.67 times 10 to the... So negative 11, positive 9, that's 10 to the 20th difference. One of the things you need to realize is electricity is far stronger than gravity. Gravity's weak. Electricity, electromagnetism is 10 to the 20th times as strong as gravity. It's easy to overcome gravity with some electrostatics. And then in our equation, Q1 will be the charge of the first object in coulombs. Q2 will be the charge of the second object in coulombs, and they will exert a force on each other. Now, force is a vector. If you're really observant, you may notice, Ben, I didn't put a vector symbol right there, and that's because it's a scalar equation. We decide the direction of the force by using like charges and unlike charges. Put your pencils down, look up. Example 7. Find the direction of the electrical forces, it says, on the positive Q charge. Let's assume this is meant to be a square-ish. Does it look like a square on your diagram? Okay, I need to revise this because let's assume that this distance and this distance are the same. Don't mark it up. Let's just assume it's a square. We're going to use something that we've sort of mentioned before. It's called the Principle of Superposition. And what it says is we have to look at 2 charges at a time. There's no way to look at all 4 of these at once. It wants us to find the direction of the force on this charge here. What I'm going to do first is look at these two charges. Which way will this charge feel a force because of this one? Will it get attracted down or will it get repelled up? Attracted down because unlike charges. So let's draw a little force vector diagram like that. Now let's look at these two. Which way will this object feel which way will this charge feel a force because of this? Will it be attracted to the right or will it be repelled to the left? So it's going to feel a force that way, and let's assume the distances are the same, so the forces are the same. So draw your arrow roughly the same. What about these two? Which way will this positive Q charge feel a force because of this one? Down and right towards attract or up and left repel away? Now, I'm going to argue that that force isn't going to be as big because this is definitely the biggest distance. So what would the net force direction be on this? How many vectors do I have here, Danielle? Let's add them tip to tail. It's going to look like this. Here's the first vector. Here's the second vector, tip to tail. And I guess the third one, we would go part ways back, but not all the way back. The resultant is always from the tail of the first to the tip of the second. There would be the net force. So right at the beginning, if we nailed or stapled these three charges in place, not letting them move, this charge would get attracted this way, diagonally, down and right. But as it moves towards this guy, this repulsion force will be getting stronger and stronger. There's probably a point somewhere here where all the forces cancel out, where the net force is zero, probably. I need some actual numbers to be able to crunch that and convince myself of that. To solve force problems, yeah, there's still more, Danielle. We're going to finish it part 2 on Wednesday. So part of what you'll miss is the part 2. To solve force problems, step 1, we need to express our charge in coulombs. Why did I add that? Almost all the time, I'm going to give you a charge in microcoulombs, once in a while in millicoulombs. I think in one question in nanocoulombs. I'll almost never give you a charge in coulombs because that's bad. Then we're going to substitute the charges and the distance into the Coulomb's law to find the magnitude of the force. To find the direction, we're going to use the concept of like charges repel and unlike charges attract to find the direction. And if there's more than 2 charges, we'll do the charges 2 at a time, and we'll add each of those forces vectorially. Sam, tip to tail if they're at angles, or if they're in a nice straight line, we'll go winner minus loser if one's to the right and one's to the left. Little technical comment though, Graham. If we have unlike charges, one's positive, one's negative, then the answer we're going to get is negative, and we don't want a negative answer. The negative tells us there's attraction occurring, that unlike charges attract. We should not conclude that the force has a negative magnitude. So we shouldn't put a negative in our answer. In fact, many textbooks put absolute value signs around that. If you go back in the box here, I could have done that. I think on your formula sheet, I put absolute value signs around your Coulomb's law equation. Did I not? I think. So we're not going to put negatives or positives into the forces equations. There are some where we will, by the way, but here we will not. Instead, we'll always put the absolute value, the positive value of the charge, and then we'll figure out the direction by using like charges, unlike charges attract. Okay? Here's a helium ion. There's the nucleus. There's the electron moving around the nucleus. This is a model, but that's okay. It says, find the electrostatic force on the helium ion. Well, electrostatic force is going to be K Q1 Q2 over R squared. What was K? A lot of you will find that because it's a 9 and a 9, you'll memorize that one. It's also much easier to type than the 6.67 times 10 to the negative 11, because you just hover your thumb above the 9, scientific notation button 9. So you'll find these are a little faster to type. Let's make big Q, or Q1, let's make that the nucleus. What's the charge inside the nucleus? Well, there's 2 neutrons. What are the charges on the 2 neutrons, Justin? What are the charges on 2 neutrons? What's the charge on a neutron? I'll give you a hint. Neutron. It's neutral, so what's the charge as a number exactly? I'll give you a hint. It's a little number that I wrote right there. That number right there. Huh? 0. Neutral, neutron, neutral, neutron. Neutrons have no charge. Okay? What else is in the nucleus? 2 what? Okay, so it's going to be 2 times, what's the charge on a proton, Justin? It's elementary. No? What's the charge on a proton, Justin? It's elementary. Lorenzo figured out the dumb joke I just made. Lorenzo, help him out. Help him out. Show him where to go. It's elementary. Good. Then here we have an electron, Justin, my friend. How many electrons are there? Don't overcomplicate this. 1. What's the charge on an electron? It's elementary. And I love the fact you went, no. We're not going to put the negative in. Okay. Times 10 to the negative 19. All over. And then in brackets, they told me in the question, they told me the radius. It's 2 times 10 to the negative 11th. Don't forget the squared. I strongly encourage you all to try this on your calculator to get used to typing these different scientific notation, the expressions in. See what you get. You get 1.15 times 10 to the negative 6, I think. Is that a big force? It's gargantuan. It's huge. It's fantastically big on an electron. It's huge. F equals what? Come on, people. F equals what? If you get the A by itself, you get F over M. I actually took that force and I divided it by the mass of the electron. That electron is accelerating at 1.26 times 10 to the 24th meters per second squared. It's a massive force on the electron. Electrostatics is a huge force compared to gravity. We never get anything near that when we're talking about gravity. 9.8 as our acceleration near the Earth's surface. How about 1.26 times 10 to the 24th? Oh, that'll do it. Okay. So in atomic terms, the force that we found in example, this used to be example 3, it's example 8 now, I just realized I have to change that, is massive. It's massive, massive. I like example 9, I like example 9, I like example 9. Example 9 is the next question. We're going to pause here. On Wednesday, I'm going to finish off this lesson. I'm going to get about halfway through lesson 2. And then on Friday, I think we'll finish off lesson 2, probably. I'll also be bringing out